Hello, here's another example of a nucleophilic addition reaction. We're doing reactions of aldehydes and ketones. This particular episode is brought to you by Expo Whiteboard Care. Not really, they didn't give me any money. If you're not using Expo Whiteboard Care, your whiteboard can tell you don't care. All right, so in this case, we're going to look at a hydration reaction. So these reactions can happen without a catalyst, but if you really want it to go forward in a reasonable way, we'll use some catalytic acid. So you take a ketone or an aldehyde, both work well, react with water and some acid, just a catalytic amount of small acid, then you get this diol molecule, which is referred to as a hydrate, right? And how does that make sense? Well, you really are adding water. So bonded to this carbon is just one oxygen, right? And then we've added a hydrogen, and another oxygen, right? So we've, in net, overall, you've added H2O, right? So not a clean water molecule attached there, but in terms of atoms attached there, we've done a hydration. So this reaction is going to work a lot better with the acid catalyst. And so if you have weak reactants, weak nucleophiles, and we want to react with aldehydes and ketones, they need an acid catalyst to make them work better. It's somewhat similar to reactions of alcohols, except in this case it's not acting as a leaving group, right? So for our hydration, right, if we're just adding our nucleophile, that can work, but it creates a pretty strong base here with O-, right? So a reactant like water is not going to be a strong enough nucleophile to add there and make a really strong base from that. So that's not a very favorable reaction. So in order to make that happen, if we protonate it first, right? So do a proton transfer reaction, add a hydrogen to the oxygen, giving it a positive charge, then even a weak nucleophile can add, because then you're just having an alcohol left over. So then we have a much more stable step there. So proton transfer to make it more active, so then the nucleophile can add. So let's take a look at the mechanism for what this looks like. So water is going to react with HCl to make H3O+. Right, the only thing that can be reasonably construed as a base here is my oxygen on the carbonyl. So first we're reacting with the negative end of the carbonyl. Do a proton transfer reaction. Right, so now we have an activated carbonyl. Right, so this is going to be more reactive now, or something like water to add. Right, so hydration. Water is our nucleophile. Water is a weak nucleophile. Right, so it requires that acid catalyst in order to make it work better. Right, but now I can add. So we're most of the way there. Right, our pi bond broke, electrons go up to the oxygen, that balances out the plus charge and gives us the simple alcohol. Water is added as H2O. Right, so our water there still has that extra proton, so we need one more proton transfer step to finish the hydrate. And our reaction balances out pretty well. If we called our acid catalytic, then it shouldn't be used up in the reaction, like in the Hydrate addition or Grignard reaction. In this case, we get it back. So H3O plus is left over in the end. So really what we've done here is a proton transfer before we did our nucleophilic addition. Right, that allowed our weak nucleophile water, or in another reaction we'll see alcohols can do similar reactions. So our weak reactive water could add there, then another proton transfer, and then we've made a hydrate. All right, so this is an equilibrium reaction. I did not draw the double arrows, but for our mechanism, when we do a lot of reactions with weak nucleophiles or weak bases like water, usually there's some extra proton transfer steps involved, and this example is no different.